Feature selection by Firefly algorithm with improved initialization strategy. The authors of the paper are Timea Bezdan, Dusan Svetnic, Luka Gajic, Miodrag Živković, Ivana Strumberger, and Nebojša Bačanin. Are there any of authors here to present paper? Okay,
yes,
I believe
yes,
Luka Gajic is here.
And I can present. Our work is feature selection and feature extraction with Firefly algorithm, which is hybridized with improved initialization strategy. First thing, when we speak about feature selection, that is the process that helps to retain the most informative features from the data set. So we have data sets that have some features, and we need to extract features that are the most important for us or the work we are doing. We can do that with many techniques. In this paper, we used PCA, LDA, and TSNA. And because some of the data sets have a large number of features, that can greatly affect performance of training systems. Additionally, we can apply the feature reduction technique that I mentioned to transform existing features into more useful ones. Next, about machine learning systems. The goal here is to successfully predict the output of the algorithm for each of the inputs. So we need to teach our system with Firefly algorithm how to predict some things, something like how to predict possibility of disease in the patient and other things. That machine learning system relies on the algorithms that are based on principles from statistical and linear algebra. After that, we train that machine learning system either unsupervised or with supervised learning, and we evaluate each data set with test set, training, and validation validation set. So with the supervised learning, we map the input data to the appropriate outputs where the data sets are clearly marked. So we can use the data sets that somebody else labeled for us. They labeled which are the correct options, and the system can learn to see that correct options in other data sets, that in other examples that are not seen before. There is a solution in relation to which we can evaluate our training systems. We used two important types of supervised learning, which are regression and classification. Classification is the type of learning that deals with discrete values, also called classes or categories. And there can be multiple categories or just two of them, like binary classification, but it is always has to be a finite number of categories. Dataset is rich in information, and that drives our machine learning model. We can talk about the curse of dimensionality. That is a problem because many data sets have very, very large dimensions, and we need to extract some features so we can reduce dimensionality for better performance. First, we start with feature extraction. As I said, feature extraction is working with data sets, and we need to extract valuable features from our data sets so we can use them in the training of the machine learning system. One of the popular techniques for feature extraction are PCA, or principal component analysis. That is one of the most used linear dimension reduction technique. That technique takes original data and tries to find combination of the inputs features which can best summarize original data. So we take, for example, 3 features and summarize them in one feature, and we reduce the dimensionality of the problem by 3. Next one is TSNA. That is T-distributed stochastic neighbor embedding. That is a non-linear dimensionality reduction technique used to mainly for visualizing in high dimensionality data sets. It works by minimizing the divergence between distribution. And we used LDA, that is linear discriminant analysis. That is a supervised learning dimensionality reduction technique, and it aims to maximize the distance between the mean of each class and minimize the spreading within the class. Next step is feature selection. Feature selection reduces the dimensionality of the data or the problem, even more by highlighting a subset of features that give us far better system performance. A certain amount of information will be lost because we reduce or compress our original data set into more, I would say, performance friendly. And feature selection can be performed with 3 methods: filter method, wrapper method, and embedded method. We used wrapper method. For this work, our wrapper methods can detect connections between features, but this way of selecting features relies on searching the entire feature space, and that is very large space. So we use wrapper methods that can detect connections between features. And existing methods such as sequential forward feature selection that provides good results but have performance issues, and swarm intelligence algorithms can help us with that, because the swarm intelligence is the algorithms are optimization algorithm and can help with performance issues. So what are swarm intelligence and swarm intelligence algorithms? That are the part of the meta heuristics that are modeled on natural processes. Swarm intelligence is looking for answers in nature, precisely how nature optimizes some things. That things can be, for example, hunting behavior of some group of animals, and always there is a group. Either it is a pack of wolves, flock of birds, a swarm of insects, and the group can deal with the problems that none of the individual can. So when looking for food or running from predators or mating, the group can show a much more intelligence than each individual separated. So swarm intelligence can help us with the issues where there are many things like features in dataset or nodes in wireless sensor networks, for example. And it is sometimes much better to get practical solution than to spend a lot of time looking for the right solution. What that means? That means that swarm intelligence algorithms don't give us the right solution, the theoretical solution. They give us the approximate solution. And with that approximate solution, we can manage to get a very, very good technical problem solved. Because the search space for that problems that are almost always MP complete problems is huge, and we cannot possibly with any means, with any linear means, solve them in our lives. We use Firefly algorithm. Firefly algorithm is made by Shinji Yang in 2010 and is one of the best performing algorithms there is. Yang was inspired by fireflies, more precisely how firefly attract other fireflies. Fireflies emit light when they're attracting their mate, and for simplicity, he modeled the fireflies to have same sex, and their attractiveness to each other does not depend on their gender for model optimization and approximation. Next, the attractiveness is proportional to the intensity of the light they produce, and brightness also depends on distance between them. So brighter firefly will attract more fireflies that are less brighter than he is. And the intensity of the light produced by the firefly is equal to the objective function. What that means is that that intensity through objective function, we can manipulate that intensity of light, and through each generation, we can optimize more and more our problem. We used Firefly with improved initialization strategy. We will see Firefly algorithm in the coming slides. This is just introduction. We used the Firefly with improved initialization strategy, and it was noticed that the search process of the original Firefly can be stuck in suboptimal domains because generally problems have local minimums or local maximum depending on the are they minimization or maximization problems, and sometimes the algorithm can be stuck in one of those local extremum. Original Firefly does not incorporate a separate exploration procedure and diversification, and is guided and controlled only with step size alpha. That is a step used to model moving of the firefly by random walk. The solution of this problem can be found in quasi-reflection based learning, and that is in initialization strategy for our problem. That this is how we set up our machine learning system. Because we have to perform feature selection, we use wrapper approach and binary firefly with quasi-reflective learning initialization. We use S-shape sigmoidal transfer function that maps initial values to discrete values 0 and 1. After that, we use binary conversion, and if the output of that function is less than 0.5, we converted it to 0, and if it is greater, we converted it to 1. So we can get discrete values of 0 and 1. And the problem is set as maximization problem, and we are maximizing accuracy of our machine learning model. Also, the KNN classifier is used as a feature selection guide. On this slide, we can see the pseudocode of our hybridized Firefly. So the first thing is to generate the initial population. In swarm intelligence, we always have this initial population on which we work and which we optimize. Every member of population is, for example, some sets of coordinates in our search space. Next, we define the light absorption, max iteration. This is all set up for our main part of the algorithm. We calculate the fitness, and we move through that population of fireflies. And if in each iteration, if we see that the firefly 1 is less luminous than the firefly 2, we will move 1 to 2. So that every firefly will be attracted to the firefly with the most luminosity. And after each iteration, we rank our fireflies and find the current best solution. On the right side, we can see the detailed description of the population size, maximum iterations, number of runs, and other parameters. So to conclude, we tested this algorithm or machine learning system on 17 well-known data sets. The hybridized Firefly algorithm achieved the best average accuracy. The second best was original Firefly, and the third best was binary gray wolf optimization method. That is the method that used the gray wolf optimization algorithm. And the Firefly and the gray wolf optimization have the best results on data sets that have more than 1,000 samples. That is the true power of swarm intelligence, because when you have many huge search space or many samples, swarm intelligence can work with that better than other math heuristic techniques. And also, our algorithm outperformed other approaches on exactly 2 M of n and waveform and clean 2 data sets. And it can be concluded that the proposed algorithm is a very promising method for feature selection. Thank you for attention. If you have any questions.
Thank you, Dusan, for presentation. Any questions? Okay, since this is the final paper, I believe we can conclude this session. Thank you all for your presentations. Thank you all for attending this. And finally, thank you, Ivan, for support on the technical aspect of session. Goodbye to all.